So again, this week we're studying direct current circuits, circuits with direct current, DC currents. And it's contained in the textbook by Bauer and Westphal in chapter 26. This is part 2 of the screencast, where we'll go over a few examples. Here's an example that we already considered in part 1, charging a capacitor. So we have here a circuit with a battery, and it will have an EMF E, some number of volts, a switch, a resistor, it will have resistance R, and a capacitor. It will have a capacitance C. So when we close the switch, current will flow. The current flows away from the positive terminal of the battery and into the negative terminal of the battery through the resistor, and then it will accumulate charge on the capacitor. So we'll end up with charge Q on one side of the capacitor and charge minus Q on the other side of the capacitor. And Kirchhoffs' loop rule says that the EMF minus IR minus Q over C is 0. And we also have a differential relation which says that dQ dt is equal to I. The rate of accumulation of charge on this side of the capacitor will be equal to the rate of charge flowing to the capacitor, which is the current I. So here's I, here's also I. There's no current passing through the capacitor because there's an insulating layer. But what happens instead is that a positive charge accumulates on one side and a negative charge accumulates on the other side. Now, we have here two equations. There's a differential equation involved. Since there's a differential equation, we have to have a boundary condition, and we'll say that Q at time 0 is 0. So in other words, we start with the capacitor with no charge separation. And then the solution is C times E times 1 minus e to the minus t over tau, where tau is the so-called time constant. It's R times C. R resistance times C capacitance. So that has units ohm, farads, and that has the units of time. Now that's the charge on the capacitor, and the current is the derivative of that, will be E over R, e to the minus t over tau. So the current starts out at a value E divided by R, and then it decays exponentially until it goes to 0 with a time constant of tau. We can verify that this solves the equations. We can verify, well, we went over the solution in part 1, but we could verify it with a little computer program. If I type in the function Q, so this is using Wolfram Mathematica, so Q is C times E, 1 minus the exponential minus t over tau, tau is RC, I is Q prime of t, so that's Q, this is I. You see what it is, it's V over R, e to the minus t over tau. And we can test whether that satisfies the differential equation. We can calculate EMF minus IR minus Q over C and simplify the result, it's 0. Verifying that these are the correct solutions. Well, that's the simplest example of charging a capacitor. It's a problem with exponential time dependence. All right, now let's consider an example which is more complicated. Charging two capacitors. Two capacitors sort of in parallel, so not exactly in parallel because of this resistor, but kind of in parallel. So again, we have a battery which is connected to two capacitors. And the connection goes through a resistance R, and the two capacitors are separated by a resistance small r. So when we connect the battery, there'll be a current coming out of the positive terminal and going into the negative terminal. And we'll call that current I1. Now, at this junction, the current I1 will split into two parts. So there'll be a current over here and I'll call that I2. So here there'll be a current I2. No, I'll call that one I3. So here's I1, here's I3, and there'll be another current here, which I'll call I2. So I hope you're taking notes so that you can recall what this calculation is doing. The battery supplies current, a direct current, and we'll call that current I1. When it reaches, the current at this junction will be I1 coming into the junction and I2 and I3 going out of the junction. So the current sort of splits here into two parts, I2 and I3. Now here again, there'll be a current I2. Any current that goes into a capacitor, an equal amount of current must come out so that the capacitor doesn't become charged. Of course, the charge is separated, so we'll have a charge separation here. And let me use a different color. For the charge separation, we'll call the charge on the upper plate Q2, Q1. And then the charge on the lower plate is negative Q1. So as a current I2 comes into the upper plate, a charge Q1 begins to accumulate. And so that the net charge on the capacitor remains zero, an equal amount of charge I2 must leave the lower plate, leaving the lower plate charged minus Q1. And similarly, this capacitor will become charged, and I'll call those charges Q2 and minus Q2. So in all these circuit analyses where you have multiple circuit elements, multiple resistors, multiple capacitors, and so on, the first thing you have to do is label the various currents and charges. So I'm labeling here three currents, I1, I2, I3. And I'm labeling two charge separations, Q1 minus Q1 on the capacitor C1, Q2 minus Q2 on the capacitor C2. All right. Now we start writing down equations using Kirchhoffs rules. So Kirchhoffs' junction rule applies at this point where there's a junction, and at this point where there's again a junction. But we don't really have to have two equations. We really only need one equation because the equation would be the same at both junction points. So let's take this junction. Current I1 comes into that point. Current I2 and current I3 goes away from that point. Therefore, by conservation of charge, I1 is equal to I2 plus I3. So that's one equation. There's a similar equation for this junction point, but I don't need to write that down because that's just the same equation. Now, there have to be relationships between the currents and the charges. So again, looking at the picture here, Q1 comes from the current I2 flowing into the capacitor and away from the capacitor. So dQ1 dt is I2. Or using the dot notation, derivative with respect to time is a dot put over the symbol. So dQ1 dt is Q1 dot is equal to I2. Now I might as well save myself a little writing by replacing I2 by I1 minus I3. So this capacitor becomes charged by the current I2. The rate of charge delivered to the plate is I2. That will be dQ dt. Now as for the other capacitor, it's just the same, only the current which is delivering charge to this capacitor is I3. So dQ2 dt is I3, or Q2 dot is equal to I3. All right, so that's the junction rule and the differential relations between capacitor charge and current. And now I have the loops. Kirchhoffs' loop rule says the change in the electric potential, change in voltage, across a section of a loop, the sum of those is 0. So as the first loop, let's consider this loop. I have delta V across the battery plus delta V across this resistor plus delta V across this capacitor is 0. Now delta V across the battery is E. Delta V across this resistor is minus I1R. Why is it negative? Well, because I'm calculating the change in potential going this direction. This will be the low potential side. This will be the high potential side, so that current is going through to the right. So the low potential minus the high potential will be minus I1R. And then finally, I have the change in potential across the capacitor. Well, the change in potential across the capacitor is the charge divided by the capacitance, the separated charge divided by the capacitance. So it'll either be plus or minus Q1 over C. Now, which is it, plus or minus? Well, again, this will be the high potential side, the positive side. This will be the low potential side, the negative side. So the change is negative from high potential to low potential. So the change in potential here will be minus Q1 divided by C. So I have E minus I1R minus Q1 over C is 0. That's for this loop. Now I have to have a second loop. And I have several choices. Well, I have two choices. I could either use this big loop, the change in potential around this whole rectangle has to be 0, or I could use this small loop. The change around this loop has to be 0. And it'll be simpler if I use the smaller loop. and calculate the change of potential as I go from this point back to the same point. So first of all, there's the change of potential across the capacitor. That will be Q1 over C1 positive because I'm calculating the change. So this is the high potential side minus the low potential side. The difference will be positive. So I'll have Q1 over C1. And then I have minus I2R. And then I have minus Q2 over C2. So I'll have plus Q1 over C1 minus I3R. This is I3, remember. I think I may have said that wrong. Minus I3R minus Q2 over C2, that's 0. So I have two equations from Kirchhoffs' loop rule. And I sort of have, well, I have multiple unknowns. I mean, the unknowns are I1, I2, I3, Q1, Q2. I have a lot of different unknowns, but I have also these relations. So it really now just comes down to a problem in algebra and then calculus to solve these, really it's these various equations. Now we can start by eliminating Q1 using equation 2. We see from equation 2, Q1 is equal to I3R times C1 plus Q2 over C2 times C1. So Q1 is R C1 I3 plus C1 over C2 Q2. So that I can substitute back. Here it is again. Q1 is R C1, well, I3 is Q2 dot. So we'll write everything in terms of the Q1 and Q2. So I3 replaced by Q2 dot. Here's again Q2, C1 over C2, Q2. Now I'll insert that value of Q1 back into equation 1 here. So I'll now have E, well, let's say E is equal to I1R plus Q1 over C1. So here's E, here's Q1 over C1. Now I want I1R. I1 is Q1 dot plus Q3. So here's I1, Q1 dot plus I3, using this equation. So I've eliminated I everywhere. I've replaced it by Q. So this I1 I've replaced by Q1 dot plus Q3 plus I3. Okay, now I3 is Q2 dot. So I'll put in place of I3 Q2 dot. I have Q2 dot times R. Let me factor out a factor of R. I have Q1 dot times R, or factoring out the R, Q1 dot times 1, Q2 dot times 1. I also have Q1 dot times R, but I factored out the R, so I'll have Q1 dot. Now Q1 dot is RC1 Q2 double dot. So I'll have RC Q2 double dot plus C1 over C2 Q2 dot. So I'll have plus C1 over C2 Q2 dot. So that's this first term on the right-hand side. You see it has a common factor R. It has I3 plus Q1 dot. I3 is Q2 dot, that's here. Q1 dot, by this equation, gives me Q2 double dot and Q2 dot. So here's the term with Q2 dot, here's the term with Q2 double dot. So I hope you're taking notes and you can sort of follow along in the calculation as we go. All right, so that's I1R. Now I have to have Q1 over C1. Well, Q1 I already have here. So it's 1 over C1. Q1 is R C1 Q2 dot plus C1 over C2 Q2. And let's kind of collect the various terms. I have E, not E the electric field, but E the EMF of the battery. E is, well, I have this term Q2 double dot. R C1 Q2 double dot. And then I have these various terms. So there are two terms which involve Q2 dot. I'll have R times 1 plus C1 over C2 Q2 dot. And I'll also have R, the C1s here cancel, Q2 dot. So I have R times the quantity 1 plus C1 over C2 plus little r Q2 dot. That's these two terms. Then I have a term which goes like Q2. I have C1, the C1s cancel, so I just have Q2 over C2. It's a second order differential equation because it involves the second derivative with respect to time. All right, so this is a little more involved problem than I had for just charging a single capacitor because I have a more complicated differential equation to solve. All right, now here's the equation that I had on the previous slide. That second order differential equation for Q2. And now I want to solve that. Well, if I try to solve this in complete generality, it's going to be rather complicated. So let's do some simplifying assumptions, or simpler cases. So let's do special case with R equals 0. Remember, we had this resistor R, which was connected to the battery. And we also had another resistance, little r, which separated the two capacitors. Well, okay, let's try as a simpler case. Let's try the case where little r is 0. So I just have the battery resistance, C1 and C2. In this case, C1 and C2 are perfectly in parallel. And no resistance between the two capacitors. So that's kind of a special case. We can sort of see from the picture, C1 and C2 are going to be exactly alike. So here's C1. They sort of appear in the same way in the two problems. So there's C1 and C2. In fact, I could treat these as two capacitors in parallel and just write an equivalent capacitance. The equivalent capacitance would be C1 plus C2. But let's go on with this general equation and simplify it by setting R equals 0. So this term will be 0. It'll no longer be a second order differential equation. And this term will be 0. I'll just have E is R1 plus C1 over C2, Q2 dot, plus 1 over C2 Q2. Or I could multiply both sides of the equation I guess by let's see. I could introduce a time constant C1 plus C2 times R. That would be the natural time constant since these two form an equivalent capacitance, C1 plus C2. So let's put that in and replace Q2 dot by tau times Q2 dot. So you see tau is R C1 plus C2. So this will be tau divided by C2. Now multiply both sides of the equation by C2. So on the left-hand side, I'll have C2 times the EMF. On the right-hand side of the equation, I'll have R times C1 plus C2, Q2 dot. That's tau Q2 dot, so that's over here. And I multiply the equation through by C2, so this last term will just be Q2. And that combines with Q2 dot. So you see the equation has now simplified. It's only a first order equation now. And in fact, it's just like the equation for charging one capacitor. Q2 will be C2e 1 minus t over tau, 1 minus e to the minus t over tau. Q1, I have to go back to my equations from the previous graph and relate Q1 to Q2. I go back here. If R is equal to 0, then Q1 is just C1 over C2 times Q2. So just multiply Q2 by C1 over C2. Q1 will just be C1e times 1 minus e to the minus t over tau. So that gives me the charge as a function of time for each capacitor. And I could also get the currents just by taking derivatives of those. Now, if I make a graph of Q1 as a function of t in units of tau, so I'll plot it as a function of t divided by tau. Tau is this combined, it's the time constant for the combined capacitance. Then I see Q1, I guess that's the blue one, starts at 0. Times 0, 1 minus e to the 0 is 0. So Q1 starts at 0, and then it rises and levels off at C1e, or C1 times the voltage of the battery. The battery has some voltage V. So there's Q1. Q2 is really the same function, except multiplied by a different constant. So C2 looks like this. It levels off at C2 times V. So you see the two curves look essentially the same. They just differ by a constant factor. That's when you have no resistance between the two capacitors. All right, now let's go back to the more general case and put in some capacitance between the two plates, but not keep it completely general. Let's suppose that little r is equal to capital R. So in the first special case, little r was 0. In the second special case, little r will be the same as capital R. And now again, to make it a little simpler, let's say the two capacitances are equal. So C1 is C2. We'll just call that C. Well, now what's the equation? Well, okay, so here's R squared C. Let's divide both sides of the equation by R squared C. So I'll have Q2 double dot. Here will be Q2 dot times R times 1 plus 1 plus 1, because little r is the same as capital R. So this will be 3 R, and I divided through by R squared C1, R squared C. So this will be 3 over RC Q2 dot. And then this final term, which goes like Q2, will be 1 over C, but I divided it through by R squared C. So this will be 1 over RC squared Q2. And that whole thing is equal to E, but I divided it through by R squared C. So E over R squared C. So now the differential equation has that form. It's still a little complicated because it has a second derivative. Now, if you've studied differential equations, you know how to solve a linear differential equation. There are general techniques for solving linear differential equations. You find a particular solution. A particular solution would just be constant Q2, because then these two terms would be 0, and the constant would have to be E times C. So here's a particular solution. That's C times E. That solves the differential equation. But it doesn't solve the initial conditions. Because remember, the initial conditions are Q1 and Q2 are both equal to 0. We start out with the capacitors not charged. All right. Now, I also need a solution of the equation with no inhomogeneous term. That will be of the form e to the minus p times t. And if I plug that into this equation and set the right-hand side equal to 0, I find p can be 3 plus or minus the square root of 5 over 2 times 1 over RC. So there are actually two solutions with the right-hand side set equal to 0, corresponding to P1 and P2. And in general, Q2 at time t will be the particular solution plus alpha e to the minus P1 t plus beta e to the minus P2t. And you have to satisfy the initial condition. So Q2 at 0 would be alpha plus beta plus CE. That has to be equal to 0. That's the initial condition. I haven't yet figured out what alpha and beta are. I'm coming to that. Now remember, Q1 was related to Q2 dot and Q2. Q1 was RC Q2 dot plus Q2. And we had the initial condition, Q1 at 0 is also equal to 0. So that means that if I look at this and I differentiate Q2, I'll get P1 alpha and P2 beta, minus P1 alpha minus P2 beta. Times RC at t equals 0. And Q2 at t equals 0. But I already know Q2 at t equals 0 is 0. So Q1 at t equals 0 will be RC minus alpha P1 minus beta P2. That also has to be 0. So here's one boundary condition. Here's another boundary condition. Initial conditions at time 0. Well, now you see I have two equations with two unknowns, alpha and beta. So I can solve for alpha and beta. All right, so there's a bit of algebra and calculus here, but in the end, I'll get Q1. Well, let's take Q2. Q2 will be alpha e to the minus P1 beta e to the minus P2t plus CE, where alpha and beta have been determined. And now let's plot Q1 and Q2. So here are the graphs of Q1 and Q2. I guess the orange graph is Q1. No, the orange graph is Q2. The blue graph is Q1. Remember, C1 was the capacitor that's closer to the battery, right? We had the battery here, and then we had C1 here, and then we had C2 here. So here was C1, here was C2. there was a resistance R here separating C1 from the battery. There was also a resistance R here, because I set little r equal to capital R, separating C2 from the battery. So you see, electrically, C2 is closer to the battery than C1. So it should charge faster. And you see, Q1 approaches the final value more quickly than Q2. Q1, the charge on the first capacitor, the one closer to the battery, gets charged quicker than Q2. In this case. And they both converge to, well, let's see. They both converge for large times to C times E. When T is large, Q2 is CE, Q1 is also CE. So they'll both converge to the same value. This is, well, I call it 1 here, but it's really C times E. So that's how one would go about analyzing a two-loop circuit. And there'll be some examples like that on the Law and Kappa assignment. All right, let's examine one more case. It's another two-loop example. It's a little simpler than the previous one. In the previous two-loop example, I could have 2 resistors and 2 capacitors with 2 loops. Here I'll just have 1 capacitor, but with 2 loops. So I have a battery with some electromotive force. Sometimes I call that E, but sometimes I call that V, or to differentiate it from other voltages, I might call it V of the EMF. You know, EMF has the same units as voltage. It's volts. Battery has some number of volts. So that's the battery. Then I have a resistor, R. Then I have the capacitor is now connected here, and another resistor is connected over here. So you see I have, again, 2 loops with 2 resistors and 1 capacitor. So this will be a little easier to analyze, but let's just write down the equations. We have Kirchhoffs' loop rule for the first loop. Let's say there's a current. Let's assume it's, clockwise. After all, this is the positive side of the battery. This is the negative side of the battery. So the positive electrode will send a current off in this direction. There'll be a current coming into the negative electrode. So let's take a current in this direction, I1. And then there'll be a different current, I2. So here's I1. Here's I2. Now, there'll be a third current here. And we'll call that, I guess, I3. So, Kirchhoffs' loop rule for this loop says E minus I1R minus Q over C is 0. I go around this loop, change of potential here is E. Change of potential here is minus I1R, negative, because this is the high potential side, this is the low potential side, driving current in this direction, minus Q over C. Q over C is the potential across a capacitor. It's negative because this is the high potential side, the positive charge. This is the low potential side, the negative charge. So the change in potential is negative, Q over C. So V minus I1R minus Q over C is 0. So that's one of our equations. Now I have another loop equation, and I could use this as the loop because this has only two circuit elements. The change in potential across the capacitor in this direction, because now I'm going around the loop in this direction, I'll calculate the loop. I'll calculate the change in potential from here over to here, down to here, and back to here. So I'm going around the loop in the clockwise direction. Across the capacitor, the change in potential is plus Q over C. This time it's plus Q over C because it's the positive side minus the negative side. This is the high potential side, this is the low potential side, so the change in potential here is positive, going around the loop in the clockwise direction. Here, the change in potential is minus I2R. Because again, driving a current in the I2 direction, so as I go from here to here, the change in potential will be negative. This is the high potential side, this is the low potential side. So Q over C minus I2R is 0. Now I have another equation from Kirchhoffs rules. I have Kirchhoffs junction rule. I can put the junctions in a different color. I have a junction here where I have current I1 coming in, current I3 plus I2 coming out. So here's I2. I2 is coming out. Here's I3. I3 is going this way. I could have guessed I3 would be going in the other direction, but it doesn't matter. I'll just take it to be I3 is the current going to the capacitor. To the positive plate in the capacitor. And the junction rule says I1 has to be equal to I2 plus I3. So there's the third equation from Kirchhoffs rules. You see, before I can really write down the equations, I have to define what I mean by the currents. Current I1 is a clockwise current in this loop. The current I2 is a clockwise current through this resistor. The current I3, the way I defined it, is a current entering into the capacitor, into the top plate of the capacitor. And I've also specified that the top plate is the positive plate and the bottom plate is the negative plate. So you have to first set up this set of currents and charges. Then you can start writing down the equations. Now I have to have a third equation because I have three unknowns, I1, I2, and I3. But you see, Q and I3 are related. dq dt is equal to I3. So that's the differential relation. It says whatever current comes into the top plate of the capacitor accumulates on the top plate of the capacitor. So dq dt, rate of change of charge coming to the top plate of the capacitor, is I3. I guess I really should say I have four unknowns. The unknowns are I1, I2, I3, and Q. So I have four quantities to solve for. I1, 2, 3, and Q. Well, I'm going to need four equations. So I have three equations from Kirchhoffs rules plus this differential relation. Now again, it'll be a differential equation, so I have to have a boundary condition. In this problem, I only need one boundary condition. I just need to say that, let's say at time 0, the capacitor is not charged. So let's say at time 0, I attach the battery, and at that time, the capacitor is not charged. So I have this initial condition, Q of 0 equals 0. All right, so that sets up the problem. I'll let you work on the math part of the problem, which is just to solve these various equations. You see how you can solve these equations. First of all, using this equation, you can eliminate, let's say, I2. I don't really want to eliminate I3 because I have Q dot is equal to I3. But I could eliminate I2. I could just replace I2. Where does I2 appear? Here. I could just then replace that by I1 minus I3. And then I3 is Q dot, so I could replace I3 by Q dot. Well, you kind of have to put the various equations together and reduce it down to a differential equation, which you then have to solve. So I won't work that out here in the video. I believe this problem might be one of the ln kappa problems. I'm not sure. But anyway, this shows how to set up the problem. It's a matter of Kirchhoffs rules, differential relations relating capacitance, the charge on a capacitor to the current entering the capacitor, and maybe initial conditions. So that ends the videos. Now you should be prepared to go back and do the ln kappa exercises. And if you need more, more examples, you can look in the textbook on